I thought I'd do another version of the same problem, but I wanted to calculate the moments a little differently to help drive home. You can take the moment anywhere and get the same answer. And so last time we took it at B and worked out to 740 newtons. And let's try it again, taking it at A. And now looking at A, we're going to lose the 300. So we look down at our forces. These end up being 100 newtons up. This is 400 newtons down. So I'm going to still say it's a clockwise motion. We've already proved that in the last problem, but how you can just kind of look at the beam and guess which way it's going to go. Now, because we're taking the moment at A, we don't have to calculate the 300 newtons here. So now we have the first force we come upon is 400 newtons, and that is pushing down. And if you're pushing down a lever, turn it this way. So we'll say that distance times force is 3 times 400, and it's positive. Now, when we get to the end of the lever, we have 400 newtons going up and 300 newtons going down. And so you just find the difference of the forces, and that'll equal 100 newtons. I think you can do that math in your head. But it's going in the up direction. It's 100 newtons up. So if you're pushing your lever on a pivot and you were pushing it up, it would go counterclockwise. So that's opposite of our convention. The distance is 5 meters, so it'll be minus 5 times 100. And then we have our upward shift of the 200 newtons because the plane that we're taking our moment at is up here, our x-plane. So we got to get this up here with the rest of them. And so that's a plus 0.2 times 200, because that's our height. And then we calculate that, and we get 1200 minus 500 plus 40 equals 740 newtons. And it's the same, you just, like I said, you can take them anywhere you want. And to prove that, we'll do it one more time, and we'll call this point C. And I don't know why you would ever want to take it there, but how we're going to visualize this is that this is point C, and here's our beam, and now with the 300 newtons up here, we're going to get a twist of that around this C axis, and now we remember our 100 newtons up here. Well, that's opposing, and then of course we still have this 200 newton shift. So let's calculate that. So MC, we know it's clockwise, equals 300, 3 meter shift. It's our distance from this new point of rotation. So 3 times 300, and we don't have to calculate 400 because it's on our axis of rotation. Then we have minus 2 times 100, and then our upward shift to get that 200 on our on an appropriate plane, and of course that's 900 minus 200 plus 40 equals 740. So like I said in the beginning, you can take them anywhere, but as the problems get more difficult and have more forces and more variables, you really want to be picky where you take your moments. And the part that I was really sloppy on at the end of the last video was, say you have your beam and you have some force at, say, 30 degrees coming off. Now this is a more obvious one. We would know that the sine of 30 is going to be calculated in our moment because that it's giving us upward direction. But if it is kind of confusing for whatever reason, maybe you got something like this, and you're not quite sure whether to use sine or cosine, what you do is, like I showed in the last video, is you box out your vectors, you take a horizontal axis for wherever that they're connected to, and then because this is going in this direction, you put your vector here, and here's your other vector, and this is equivalent, since the y direction, which would cause upward motion on this, it's either sine of 30, or using your knowledge of triangles, this would be 60, or cosine of 60 is what you would use in your moment. And this will help you figure out which one to use. And of course, depending on your convention, is whether you'll add or subtract that force value. And I think that covers the basic concept of torque and momentum. I'll try to do some more difficult problems when I get back on Sunday or Monday. But if you have any questions, feel free to text me.